Okay, so this is all great and everything. The fact that we can approximate the distribution of p hat with the normal distribution. This is a very useful property that we have, except there is a limitation, and that is in order for the normal distribution to be a good approximation, a few properties have to be true. Okay, so we have what we call conditions to use the central limit theorem. So conditions to use the central limit theorem, meaning if the following conditions are not met, okay, we cannot approximate the sampling distribution with the normal distribution. Okay, so these are the three conditions. We've got what we call the random and independent condition. This means that the sample that we are looking at, the sample has to be selected at random, has to be selected randomly. And individuals must be selected independently of each other. Okay, from a practical level, basically if we know that the sample is selected randomly, then this condition will be met. Right, we have the large sample condition. Okay, basically the sample needs to be large, it can't be too small. All right, how do we check to see if the sample is large enough? So we must see at least 10 successes and at least 10 failures, okay? So there must be at least 10 successes and at least 10 failures. If the counts are not given, if the counts of successes and failures are not provided, then n times p and n times 1 minus p must both be bigger than 10. And then lastly, we have the big population condition. And for the big population condition, the population needs to be big. All right. Basically, the population must be at least 10 times larger than the sample. Or conversely, do not sample over 10% of the population. Okay, good? All right, so let's just try out an example here. Let's say I take a random sample of, we'll say, 50 students at an elementary school. We'll say the elementary school has 680 students enrolled. Okay. In the sample, we'll say 84% of students participate in extracurricular activities. Okay, so we'll say, are any of the conditions violated? If so, which? Okay, go ahead and take a minute to see if you can identify which, if any, of the 3 conditions are violated. Do we have an answer? Okay, let's take a look. Okay, so random and independent condition. Okay, well, when we read the problem that says we take a random sample of 50 students. So this condition is met. Okay. What about the large sample condition? All right, how do we check the large sample condition? We need at least 10 successes and at least 10 failures, right? All right, so when we look at our sample, we don't have the actual counts. So we're going to have to check n times p has to be at least 10, and n times 1 minus p has to be at least 10. Okay, so let's see. N is 50, and p is 0.84. So 50 times 0.84 is, what is that, 42? So that's bigger than 10, okay? We do 50 times 1 minus p, which is going to be 0.16, and this is 8. Okay, so this is 42 is bigger than 10, but 8 is not. Okay, so n times 1 minus p is not greater than 10, greater than or equal to 10, so this condition is not met. Okay, let's take a look at the last condition, big population condition. All right, so what is the size of the population? So the population has 680, and our sample has 50. Okay, so 50 times 10 is 500. 680 is bigger than 500 is greater than 500, so our population is big enough. So that condition is met. This is okay? Are there any questions on this? So we want to, be able to go through a problem and make sure that the conditions are met. So you can expect to see a few questions like this on next week's quiz, where I'll kind of list off a scenario and I'll say, are any of the conditions violated? And if so, identify which condition is violated. Okay, and make sure you don't mix up. Common mistake is students mix up large sample condition and big population condition. Large sample condition means the sample itself has to be large enough. Okay, you need to have at least 10 successes and at least 10 failures in your sample. The big population condition means your population needs to be big enough, meaning it has to be 10 times bigger than the sample. Is this good? Do we need another example, or are we okay? We're okay. All right. Okay. All right, so the last topic that we're going to cover today is called a confidence interval. Okay. So a confidence interval is one way for us to look at the data and make a conclusion about the population. Okay. So this is one method, one statistical inference method. Okay. So when we introduced the topic of sampling distributions using the Reese's Pieces, we said that we have a machine and we're going to draw a random sample out of the machine, okay? But in that scenario, I said we knew that in the machine, we knew that exactly 30% of the candies are orange, okay? The only way we'd know that exactly 30% of the candies are orange is if we counted up every single candy in that machine, okay? And that would actually be a lot of work to do. And usually, when we have the population, we're saying the population is too big for us to observe directly, okay? So just imagine a more likely scenario, okay, where maybe you've got the big machine. Maybe this time we'll put M&Ms in here, okay? So we'll say, you know, we got candies in the M&M machine. Okay, so just imagine thousands of M&Ms in here, okay? So a machine full of M&Ms. Okay, and we want to know what proportion of the machine, or what proportion of the candies are red. All right, so what proportion of the candy pieces in this thing are red, okay? So machines full of M&Ms, like thousands or, you know, hundreds of thousands of M&Ms, okay? Thousands and thousands of pieces. Okay, so without counting all of them, can we estimate the proportion that are red? Maybe, all right. So let's say we're going to take a random sample. We'll say 200 pieces of candy. Okay, so we take a random sample of 200 pieces of candy. And in our random sample, we'll say 36 pieces are red. Okay. So my sample proportion is what? Sample proportion is p hat equal to 36 over 200, 0.18, okay? So my sample proportion is that 0.18 of the candies in my random 200 pieces are red. What does this say about all the candies in the machine? Does it mean that if I counted up all the pieces in the machine, I would get 18% red? No. Okay, not necessarily. I mean, it could be, but not necessarily, right? Could the proportion of red pieces in the machine be 20%? Could it be 15%? Could it be 25%? Maybe, okay. So what can we say about the proportion of candies in the machine? Can we say anything? Yeah, okay, we would expect that the proportion in the machine is something around 18%, but it could be much higher, it could be much lower, right? Okay, so this is kind of the idea that we are getting at with a confidence interval, okay? Is that, so we would expect the proportion, I'm going to say that the proportion of red pieces, P, is around 0.18. But it could be higher, it could be lower. All right, is this okay? All right, let's say, okay, so put that thought on hold, okay? And let's say someone shares this picture on, I don't know, Facebook or Instagram or something, Snapchat. Okay. All right, what's it a picture of? It's a picture of a dog on a football field at the 30-yard line, okay? Huh? You can't tell? It's not clear that this is a picture of a dog? Yeah, okay, it's very, this is the best art you'll see.
The 30-yard line's right in the middle.
Huh? Yeah.
The 30-yard line's right in the middle.
Yeah, yeah. I mean, it's not the whole football field. I mean, you're gonna have the 40 over here, okay? LA has a football team, man. That's exciting. So we'll see. We'll see how. I have not followed football, so this will be new for me. Okay. All right. Okay. So anyway, it looks like a dog at the 30, right? Okay. So dog is at the 30. Okay, but then it says, but he has an invisible owner. This is for real, okay. Invisible owner with an invisible leash. Okay. All right, so the dog's going for a walk. He's got an invisible owner with an invisible leash, okay? And we want to know, where is the owner? Okay. This is what we want to know. So we see the dog at the 30, but we want to know, where is the owner? And the owner is invisible and has an invisible leash, okay? We do know a few things about the behavior of the dog, okay? It's an elastic leash. The leash is elastic. And we know about the behavior of the dog. Okay, in that the dog doesn't like to pull too hard against the leash. The dog doesn't like to get choked. So we'll say 68% of the time the dog is within 1 yard of the owner. And we'll say 95% of the time the dog is within 2 yards of the owner. And 99.7% of the time dog is within 3 yards of the owner. Okay? Now technically, because the leash is elastic, the dog could be 4 yards away from the owner, but this happens very rarely, okay? This means the dog was really, really intent on getting far away from the owner that time, okay? It happens, but it happens very rarely, okay? Leash is elastic, so dog could be 4 or more yards away from the 4 or more yards from owner, but this rarely happens. Okay. Does that kind of make sense? All right, so if we see the dog at the 30, what can we say about the location of the owner? So the dog is at the 30. What can we say about the owner? Okay. Yes, I mean, so we can say, you know, the owner is very likely to be between 27 and 33. Could the owner technically be at the 34? Could be. If that were the case, we would be surprised because that means the dog, this picture was taken at one of those very rare occasions where the dog was more than 3 yards away from the owner. But it is technically possible, okay? So kind of what, we're going to kind of go for the middle and we're going to say, I am 95% confident that the owner is between the 28 and the 32. 32 yard lines. Does that make sense? So we're allowing for the possibility that the owner is outside of that range, okay? Because that could very well be the case. But based on our knowledge of the behavior of the dog, because we see the dog at the 30, we can be confident, 95% confident, that the owner is between the 28 and the 32. Because wherever the owner is, 95% of the time the dog is within 2 yards of the owner. Okay. Does that make sense? This statement of confidence? Okay. So this is supposed to be an analogy or an analog saying the dog is kind of like our p hat, right? We get to observe the sample proportion p hat. Okay? The owner, which is unknown to us, the location of the owner is unknown. That's like the p that we do not know. And the fact that we know the behavior of the dog, or the behavior of p hat, okay? From the central limit theorem where we said p hat, the sampling distribution of p hat can be approximated by the normal distribution, that tells us about how p hat behaves around p. Okay, and so this is the, the central limit theorem, which says the sampling distribution of p hat is normal. All right, is this okay? So tying this back to what we have, all right? So we know that the behavior of p hat follows the normal distribution with a mean equal to p and standard deviation or standard error equal to the square root of p times 1 minus p over n. Okay, so based on this, okay, we can say that, you know, about 95% of the time, p hat is within 2 standard errors of p. Okay, and more accurately, it's 1.96, but we often use 2 as an approximation, but more accurately, it's 95% of the time p hat is within 1.96 standard errors of p. Okay, so we can flip the statement around and we'll say, you know, we can say I am 95% confident that p is within 1.96, you know, almost 2 standard errors of p hat. So if we know the location of p hat, we can make a statement of confidence about the location of p. Okay, is that all right? What is the standard error? There is a slight problem though. Okay, let me just make sure you have all of this before I flip to the next slide. Okay, so the standard error for p hat is the square root of p times 1 minus p divided by n. What is p? P is the population proportion. Do we know what the population proportion is? We don't, okay? So we have a problem, okay? We do not know p. Okay, so what we do is we improvise and we use our best guess for p. What would our best guess for the population proportion be? If someone said, what proportion do you think of M&Ms are red? You would say, well, I took a sample of 200 candies and 18% of them turned out to be red. So my best guess right now is that 18% is red. Okay, so we don't know p. We're going to plug in our best guess, which is p hat. Okay, and then thanks to mathematics, this substitution is okay, all right? Later on, we do a similar substitution for sigma and things like that, and we have to compensate for it. You know, like when you do cooking, you can substitute things for that, and you sometimes you have to compensate for that in the cooking times and things like that. In this case, this substitution, it's fine. Okay, so we plug in our best guess p hat, and that's fine. Okay, so we use the standard error equal to the square root of p hat times 1 minus p hat over n. Okay, we use this when we do confidence intervals because when we do confidence intervals, we don't know what p is. Okay. Okay, so putting this all together. All right. Put it all together. Okay. So we'll say, we can make a statement like, I am 95% confident that the population proportion P is between, and what we're going to do is we're going to start at p hat, and we're going to go down basically to 1.96 standard errors. Each standard error is going to be p hat times 1 minus p hat over n. Okay, it's going to be between p hat minus this and p hat plus 1.96 times that. Does that make sense? So whereas before, with the dog, we said, we see the dog at the 30, and we know the dog generally stays within 2 yards of the owner, so we said the owner is probably between 28 and 32. Basically 30 minus 2 and 30 plus 2. Here we're doing the same thing. We observe p hat at the location p hat, and we're saying based on that, I'm 95% confident that p is between p hat minus 2 or almost 2 standard errors and p hat plus 2 standard errors. Okay, because this looks almost exactly the same, both sides of it, we can put them together. Just to save some space in our writing, and we say p hat plus or minus 1.96 times the square root of p hat times 1 minus p hat over n. Okay? When you see this plus or minus, this means that this is 2 values. One of them is p hat minus this thing, and the other one is p hat plus this thing. Okay? But I guess it saves us from writing the same thing twice, or almost the same thing twice. We just say p hat plus or minus this thing. Is that okay? And that's to create a 95% confidence interval. So let's try this out. So we'll say again, we want to know what percentage of candies or M&Ms are red. Okay. What proportion of M&Ms are red? Okay. So what we do is we take a random sample of 200 pieces of M&Ms. Okay. We find 36 are red. Okay. So based on this sample, make a 95% confidence interval for the proportion that are red in the population. Red pieces in the population. Okay, go ahead and try that out. All right, let's see how to do this. Okay, so we look at this. We take a random sample of 200 pieces of candy. So 200, this is going to be our n. We got n is equal to 200. All right, and we find that 36 are red. So we're going to have x equal to 36, which means our p hat, our proportion in our sample, is 36 divided by 200, which gives us 0.18. Okay, so we have 18% in our sample are red. And we want to make a 95% confidence interval for the proportion that are red. So we've got p hat plus or minus 1.96 times p hat times 1 minus p hat over n. So I'm just going to plug in the values that we have, which we've got them all. Okay, so we're going to have 0.18 plus or minus 1.96 times the square root of 0.18 times 1 minus 0.18 divided by 200. Okay. All right, so this becomes 0.18 plus or minus 1.96, and I'm going to go ahead and solve for the standard error here. Okay, so here, let me, so on my calculator, I can just do this. I can do, square root fraction up top. I'm going to have 0.18 times parentheses 1 minus 0.18 and close off the parentheses here. I go down and I'm going to type in 200. All right. Is that good with everybody? All right. I'm going to hit equals and I get 0.027166. All right. So I can write that here, times 0.027166 or something like that. But really, I don't even have to write that down. I can just multiply that, just hit times. It's going to plug in the answer and do 1.96. Okay. And I get 0.0532. All right. So I got 0.18 plus or minus 0.053. I'm going to just keep it there. Okay. You can keep more decimal places, no problem. Okay, so that means on the low end, I have 0.18 minus 0.053, and that's going to give me 0.18 minus 0.053, and that's 0.127. Okay, I hit this. If your calculator gives it like in this funny fraction form, you hit the SD button, and 0.127 is what we get. And then on the high end, we have 0.18 plus 0.053, which is 0.233. Okay, and so what we say is we write something like, I am 95% confident that the proportion of red M&Ms in the population is between 0.127, so basically a little under 13%, and 0.233, a little over 23%. So I'm 95% confident that the proportion of red M&Ms in the population is between 0.127 and 0.233. Does that work? Okay. It's important that we write the words, I am 95% confident. Okay. This is a confidence interval. I'm going to say a few statements that are not correct, and I'll explain why. Do we have all of this? All right. So again, the correct statement is I am 95% confident that the population proportion P is between 0.127 and 0.233. Okay? All right, things that are wrong. It is wrong to say there is a 95% probability that P, the population proportion P is between 0.127 and 0.233. Okay? Why is this wrong? It's wrong because it's talking about probability. Okay? So let me abstract this just a tiny bit. Okay? All right, I've got a quarter here. All right? I'm going to ask you a question. If I flip this coin, what's the probability that it will land heads? And you say 0.5, okay? And I would agree with you there. Okay, so I'm going to go ahead and flip it. Okay, the coin has landed. I'm going to ask you a question. What is the probability that the coin landed heads? Okay, so think about your answer there. Okay, I'm going to look at the coin now. And then I'm going to ask you the question again. What is the probability that the coin has landed heads? Okay, some of you guys are a little weirded out now. So some of you guys said answered all three questions 0.5, okay? And the truth is that the last two questions were nonsense questions. They were kind of like trick questions. Before I flipped the coin, it was correct to say the probability that it will land is 0.5 because there was uncertainty. The future had not been foretold. So it could have landed heads, it could have landed tails, and so it was fine to say that the probability it will land heads is 0.5. After the coin landed, however, there is no more probability. There's no more uncertainty about how the coin would land. So it does not make sense to ask questions of probability. You do not know whether it landed heads or tails, but that doesn't matter. It either landed heads or it landed tails, okay? There's no uncertainty. Either it landed heads or it didn't. And so at that point, it no longer makes sense to ask about probability. At that point, all you can say is, I am 50% confident that it landed heads, okay? So is the distinction there clear? You can say I'm 50% confident that it landed heads, but it no longer makes sense to say that there is a 50% probability that it landed heads. So in the same way, the population proportion P is some fixed value, okay? If we could go to the M&M's factory and say, hey, what proportion of M&M's do you manufacture are red? They could tell us, oh, that is set to be this number, okay? And that's a fixed value. If we froze time and we counted every single M&M in the world, and we could figure out exactly what proportion are red. And it doesn't matter whether we know it or not. It's a fixed value. It doesn't care what our random sample says. So It does not make sense to talk about probability that the population proportion P is between there. All we can say is talk about how confident we are, okay? So we'll say the population proportion here is a fixed value. Now, uncertainty in its value, even if we do not know what that is. Okay. It would also be wrong to say something like 95% of future samples will have a p-hat between 0.127 and 0.233. Okay, so our confidence intervals are always about p, the population proportion, and never about future samples or anything like that. Okay. Okay. Let's all right, we can have different levels of confidence. Okay. So think back to the picture of the dog with the invisible owner. Okay. So we said, I'm 95% confident that the owner's between 28 and 32. Okay. If someone said, "Yeah, I don't really like the idea of being only 95% confident. Can you be more confident? I want you to be 99% confident, or I want you to be more confident than 95%." Okay, if you wanted to be more confident about where the owner is, and you had to set up kind of a zone of where the owner is, would you make that region bigger or would you make the region smaller? If you had to be more confident about where the owner is, you'd make it bigger, right? You'd say, okay, if you want me to be even more confident that this region has the owner in it, and I'm going to go down to the 27 to the 33 or whatever, something like that, right? You'd make that region bigger. So in the same way, you can be more confident if you make the interval bigger, make the interval wider. Okay. And on the other hand, if someone says, you're giving me too big of a window, can you tighten it up and make a smaller window? You can say, yeah, I can make a smaller window, but I'm going to be less confident in my answer. Okay? So there's this trade-off. You can be more confident, but you've got to make a bigger window. You can have a smaller window, but you're going to be less confident. Okay? So, and that is all controlled by the value that we have 1.96. Okay, so we can be more confident by making a larger or wider interval. Okay, and we can have a smaller interval but our confidence level will go down. Okay, and this value, whether our level of confidence is controlled by what we call the critical value. Okay, and so what we have is we have p hat plus or minus, and I'm going to put in, instead of 1.96, I'm going to write z star, and this is called the critical value times our standard error, which is p hat times 1 minus p hat over n. Okay, and so we already know one of these critical values. Okay, so 1.96 is our z star for 95% confidence. Okay, and we have kind of 3 other values that are commonly used for different levels of confidence. Okay, so we have 1.28. This is our z star for 80% confidence. If you're willing to be less confident, you can have a smaller z star, 1.28. 1.645 is our z star for 90% confident. And then if we wanted to be extra confident, we can use 2.58. This is our z star for 99% confidence. Okay. And technically you could make a 97% confidence interval or a 98% confidence interval, and you'll end up with a different z star value. But I would say, you know, between these 4 values, this is going to cover almost every level of confidence that that people make. Okay. Generally, you don't have. No one really says, I want you to make a 92% confidence interval. I mean, it's fine. You could do that, but it just doesn't really make sense to do that, right? Like, it's like, I don't know, what would that be? I can't think of an example in real life.
It'd be like making something 97 cents.
Yeah, well, even worse than that. It'd be like, you know, going to Starbucks and saying, "Oh, I don't want a grande or a venti. I want something in between. You know, don't give me 16. I want like 17.2 ounces of coffee." And you could do it. They'd probably roll their eyes, but you know, in LA, people do their things, right? I believe, you know. So, yeah, you could go to a store and say, I want exactly 17.2 ounces of iced coffee. Yeah. Hashtag overheard in LA. Anyway, so this is these are the values that you have. So if I say make a 90% confidence interval, you do it exactly the same way before, and the only thing you change is instead of 1.96, you use 1.645. Okay, and that's fine. So you know, they're written in your book. Next week you can have a quiz. You're gonna have a quiz, and I'll have questions on confidence intervals. Make sure you write these 4 values on your quiz, okay? Or memorize them between now and next week, but probably you have better things to do with your brain than memorizing these values. So, you know, make sure you have these written on your card, okay? Oh wait, don't leave. Everybody's got to sign this attendance thing. So, before you leave, come on down and then just sign your name here. And then we'll finish, okay?